Take your seats. We're about to start the next talk in here. Really pleased to introduce Ben Nuttall. For many of you, I know he doesn't need any introduction, but Ben's been here supporting PyCon UK for several years. He's part of the Raspberry Pi Foundation, and I'll let Ben tell you more about himself and about his talk. Please welcome Ben.
Morning, everyone. So I'm going to be talking about Astro Pi and Python on the International Space Station. So I'm Ben Nuttall. I'm Program Technical Manager at the Raspberry Pi Foundation. We're based in Cambridge. I'm a creator of GPI Zero, a Python library for zero boilerplate electronics and simple electronics and project building, and a project called Pi Wheels. We automate building wheels of all the projects on Pi for the Raspberry Pi ARM architecture. Those are separate talks in themselves, but I'm talking about Astro Pi today. I write for Red Hat's community open source project, opensource.com, and this is what I look like in real life. This is what I look like on the internet, and those are some of the places I'm online. So Astro Pi. So here's the sort of summary of the talk to round it all up. There are two Raspberry Pis on the International Space Station. Kids write Python code that runs on them in space. I'm going to be talking about how that happened, why we do that, and show you some cool photos and stuff from space and a nice time lapse, and talk about how you can get involved and what's going on at the moment. So the Raspberry Pi Foundation, a lot of you will know, we're a UK-based charity founded in 2008. And since 2012, we've been selling the Raspberry Pi computer. We've sold over 27 million units to date. And those are going out to a mix of hobbyists, education users, and also into industry. The sales of Raspberry Pi fund our educational mission, but a lot of the projects that we do are sort of very separate from the hardware. We just kind of do a lot of general sort of coding clubs and things like that. So we run a lot of youth programs, such as Code Club, Coder Dojo, and competitions like Astro Pi. We have over 100 employees in the foundation in offices in Cambridge, London, Dublin, California, and India now. And in 2018, last year, we were awarded a contract from the UK Department for Education to create the National Centre for Computing Education. So we're kind of now in a position where we've been running for a few years, and we've kind of got these education programs off the ground and made a name for ourselves. And it's great that we were sort of in a position to be able to take the government's grant to roll out teacher training for new computer science teachers and lots of other programs around that. So go back to 2014. This is when the idea of Astro Pi came around. So basically ESA, the European Space Agency, they run educational programs to try and help kids get interested in space and thinking about careers in space, and that not just about being an astronaut, but about all the engineering and the groundwork that goes on to keep astronauts alive, amongst many other things, but lots of technology jobs in the space industry, and get them to think about what life in space is like and what sort of careers can be found within the space industry from an early age. Raspberry Pi Foundation also do educational programs, obviously, so we decided it would be good to collaborate on an education program and see what we can come up with. And around that time, Tim Peake, who's pictured here, was about to go up to the ISS. There was a big thing in the UK at the time that that he was going to be the first British astronaut to go up in many, many years. So everyone was really excited about it. So there was a big push in the kind of everybody was really excited. There was a big push in education. Tim is an incredible STEM education advocate as well. So he was being really vocal and being really active about getting people interested in what's going on in space. So kind of basically the whole thing boiled down to, oh, I wonder if if we're going to do an education program, I wonder if we could get Tim to take a Raspberry Pi up to the space station with him. And it sounded a bit ambitious at that time, but we started working on plans. So this is what the Raspberry Pi looked like in 2014. We were still on the Raspberry Pi 1, so this is before even the Raspberry Pi 2 had come out. So the first generation Raspberry Pi with a 700 megahertz single core ARMv6 processor and half a gig of RAM. And it looked very similar to sort of current models, but the performance was a lot worse than what we get today. We also designed the Sensehat. Hats are add-on boards for the Raspberry Pi. HAT stands for hardware attached on top. So we made a specially designed add-on board. We called the Sensehat, and it encompasses all these different sensors. So you can read the temperature, the humidity, the pressure, to get your atmospheric conditions. And there's also a gyroscope, magnetometer, and accelerometer on there, so you can sort of work out where it is in 3D space and things like that. And there's an 8x8 RGB LED display, so you can scroll text, use pixel art, pictures and animations and things. There's a mini joystick, and there's a Python library to use that as well. Now, like the Raspberry Pi, this is available as a product to buy, so anybody in the world can buy one of these and play with it and do kind of sciencey, experimenty things on it. It's a readily available device. And also the camera module. So this is the V1 camera module. So we've got a V2 out at the moment that's a higher resolution and better sensor, but this is what we had at the time. It's a 5 megapixel camera, very capable. There's a Python library written by the great Dave Jones, and there are two variations of this camera available: a visible light camera and an infrared camera. So we took those three things together. We kind of said that's kind of our offering. This is what we'd like to be able to send to space: a Raspberry Pi, a Sensehat, and a camera module. Now you kind of need to, if you have that out on the desk, it's a bit messy and there are wires everywhere and things like that. So we have to kind of think about how we're going to encapsulate and enclose this thing. So ESA sort of said to us, you need to design a case for all this to sort of sit in. Now V1 didn't really go down so well, but we ended up with this. So this is what we call an Asteroid Pi unit. So this is the Raspberry Pi, the Sensehat, the camera, all embedded in a space-grade aluminium case. And we added on some, so we stuck in a board in between the two, the Raspberry Pi and the Sensehat, to give it a real-time clock. And we wired up some big, nice clicky buttons so that you can operate the thing directly as well. And so, come 2015, we've got to send this thing to space, which basically boils down to a big stack of paper and a big rocket. Those are not to scale, but not far off. And December of that year, Tim Peat went up, and the Raspberry Pis went up in separate shuttles. But we both made it. So Tim Peat got up there, and he spent 6 months on the space station. And the two Asteroid Pi units we sent. So one had the visible light camera, one with an infrared camera. But other than that, they're identical. And basically, we sent them up. And during the time before Tim was going up, when there was this big sort of media storm around, everyone getting excited about Tim going up, during that time, we were running the first competition. So the first chance for kids to write code, which would go to space. And it was just a kind of an open call, quite a bit of a pilot, really. Can you write a program with this Raspberry Pi and this Sensehat, something interesting that Tim can play with, or that you can write messages to Tim, or something like that. It's very focused around Tim Peat being there, which was really interesting, and we had some really cool projects, and they all got some time to run their programs in space. But there was kind of it was quite a sort of limited scope at the time. We hadn't really, we did all the paperwork to get the things up into space. We got them there. We ran the first batch of programs. There wasn't necessarily a plan to to do more. There wasn't, in the initial run, it was just a case of we're going to do this one thing and do it once, and then we'll see. Later on, we managed to negotiate access to the wired Ethernet so that we could do updates. And we have to negotiate crew time to be able to move them or to push the buttons and things like that. It's a bit harder now. So Tim Peake was really involved in the mission. He was quite involved, and now he's gone. We've got to reach out to other ESA astronauts to use their time to do things, but we managed to make it work. So the Asteroid Pi competition, after the first year, we sort of designed a sort of more structured program. So we have 2 different missions. These are all open to ESA member states generally, and which is basically most of Europe plus Canada, who are a member of ESA rather than NASA. And it's all about your code in space. So we've got 2 missions. Mission 0 is really, really simple, sort of really entry-level program, particularly for younger children. And Mission 0 is kind of, I'll move on to that. Mission Space Lab is more advanced, and it's more about designing science experiments. These have been running, these kind of challenges have been running since 2015, and as I say, we have different astronauts that kind of take on the role of being the Asteroid Pi ambassador at the time. So we've had Tim, Tamar Pasquet, Alex Gers, and Fabio from representing different countries within ESA. So Mission 0, it boils down to you get 30 seconds of runtime on the ISS. And we actually had about 5,000 entries last year that all ran sequentially on the space station. So this is just kind of your Hello World program. You write that and you submit that through. There's a web emulator of the Sensehat online on Trinket IO. So you do your Python code in the browser. You hit run. You see, if you've written messages that scroll across the LEDs, you see it on the emulator. You can access the sensors, so you could read the sensors and have conditionals and show different messages according to different atmospheric conditions. You don't have access to the camera, and you can't log data or store any pictures or anything like that. So it's just a really simple thing, and you've only got 30 seconds. But we have thousands of those entries. It's just a nice, really simple activity for kids to try out. And that's what it looks like online. So Trinket IO. This competition, I should say, both competitions just opened for the year yesterday. It's a really good timing to be talking about this now. So this is now open. I'll talk about how you can get involved later, but that's what it looks like. That's the emulator. And so once you've run once your Mission 0 program has been run, we generate a certificate for you. So you've got your name and your names and your team name on the front, and on the back shows you a map showing where the ISS was over the Earth when it ran your code, because we log the timestamp and calculate the position, which is really cool that kids get, and they sort of have photos of them, standing around with their certificates saying, where the ISS was when it ran their code. So Mission Space Lab, this is a much more involved program, so it's aimed at sort of secondary school age. You're aiming to come up with an idea that you could design a science experiment that would run on the Raspberry Pis in space. Now, I should say as well, the Mission 0 is, because it's web-based, because it's part of that, using that web emulator, you don't need to do it on a Raspberry Pi. You don't need access to a Raspberry Pi or a Sensehat. It's all in the browser. But with Mission Space Lab, you're kind of designing an experiment, and you want to do a lot of testing and things like that. So we send out kits to teams that submit ideas that we deem sort of reasonable and with good scientific merit and good feasibility levels. So they actually work on the Raspberry Pi and the Sensehat for this one. There's an idea phase, so that's what's just opened. So we're now open submissions. So if you know some young people, you could get them together and have a think about what you could do with a Raspberry Pi or Sensehat, and what kind of experiment you could come up with that would run in space, and submit that idea to us and wait for the sort of judging round to determine whether you go through to the next phase. Then you go on to code your experiment. So you've got some time to work on that and develop your code. We give you an operating system image that sort of matches the versions of all the libraries that are available in flight. And you can develop on that, and then you later submit your code. Code gets checked and tested and everything, and then it gets deployed to the space station. All the programs get run. You can collect data, you can take photos, you can do all that kind of thing, and then you get all your data back. And then there's a final phase where you analyze all your data, you work out what went on and what you discovered. If you had a premise of your original experiment idea, you're sort of working on what the conclusions of that were. And then you write a report up, and then the final process is to write up your report, submit that, and we judge the reports and determine the overall winners. So there are two categories two themes of Mission Space Lab. There's life on Earth and life in space. Life on Earth is about we're using the Astro Pi with the infrared camera. You're looking, it's actually positioned out of the window so that the photos you take are looking down at Earth. And you get to log data and take photos and things. You can do kind of real-time processing on the photos as you take them, or you can log them and do post-processing down on Earth. And life in space is more thinking about, so you're on the other Astro Pi that's actually just inside. I mean, they're obviously both inside the station, but it's not pointing out the window. So you're thinking about what it's like, what the atmospheric conditions are like for astronauts, thinking about how astronauts are living and what their life is like in space. So kind of two different themes there. And you still have access to the camera and things, but you can't, for privacy reasons, you can't keep the photos that you've taken within the station. So with Mission Space Lab, you also get a certificate. Now this one has, because you've been running for 3 hours, you generally get sort of 2 passes of the Earth in that whole time. So you get a really interesting map with the path of where the ISS was for the whole 3 hours. And obviously, if you've taken photos, it's really, really interesting to be able to geolocate them as well. So the kind of ideas we get for Mission Space Lab. So a lot of people are trying to, particularly for life in space, they're trying to detect crew presence with sensors. So can you tell if the humidity rises that there's an astronaut floating past or something like that? So lots of people are interested in interaction and things. Logging data, just to see sort of if there's anything interesting that comes out. So obviously, a lot of the G-force, for instance, will be quite consistent, but then the accelerometer you might notice a spike, and you can look at the conditions that might have caused that. So sometimes they sort of put the boosters on to make a course adjustment, and it's things like that you're able to notice. And if that's the sort of thing you're looking out for, that can be really interesting. And also things like the ISS conditions. Obviously it's a very controlled environment, but a lot of kids are thinking about, we could flash the LEDs to tell them that the pressure has risen slightly or something like that. And it's interesting just thinking about what you can do and what you might want to, what might be interesting about running that code in space versus running it in your classroom, and what might be different, and what you might need to think about. And just thinking about those things is kind of what's really important to ESA, is about getting those kids considering what the conditions are like and what they need to think about. A lot of, particularly the life on Earth ones, there's a lot of kind of global issues considered. So things like climate change. People are looking at, can we identify whether there's been wildfires in certain areas, or forest depletion, greenery of plants and forest life, and things like shrinkage of lakes. So we have people kind of analyze, they've taken photos and they find archived photos, other satellite photos from past archives, and compared the size of the relative size of lakes to see if there's been shrinkage over time. And really interesting things people come up with. So they have, as I say, they have certain libraries available. So there's a library for the Sensehat I mentioned, and Pi camera, and also another Sensehat library called PiSense. They've got, so PiFM will tell you where the ISS is given with a timestamp. If you given a timestamp, so you can tell either in real time or retrospectively where the ISS was at a particular or is at a particular time. And that, in combined with a library called Reverse Geocoder we install, allows you to get the location of that position. So what the nearest city is, for instance. There's geospatial data available as well. You've got things like NumPy, SciPy, Pandas, and also kind of machine learning and things like that. So we've got TensorFlow on there, OpenCV, Scikit-learn, Scikit-image, and kids are actually using these libraries. We had one experiment last year that tried to identify evidence of wildfires using TensorFlow, and there's some really interesting stuff people can do. So a lot of people ask me things about how the process works. So the way it works is we create a custom Raspbian image with all the libraries and stuff and all the tooling that we want. So one of my main jobs, particularly this time of year, is to write the software tooling for how we launch the experiments or how we manage the processes and things like that. So we create that image with all the tooling and all the libraries installed. We send that to ESA. They do security hardening and do all their checks. We test that once it's deployed in flight. So this is actually a case of for the crew, we have to request for them to take an SD card, put it in their laptop, and use the installer the same way you would install a Raspberry Pi operating system on an SD card. Normal, just here. So we have to, request crew time for that. We get it deployed, and we have some people within ESA that have direct SSH access now that we're on the LAN, and they can log into that and perform their maintenance checks, and they can run commands and things like that for us. And we get sort of feedback from them sort of daily on what operations have been going on. We're able to then upload student code. So once the competition entries close and we've got all the code ready, we've tested it, that gets uplinked to directly to the Astro Pis. We schedule the student code to get run. And we're kind of monitoring it in real time, so we're actually getting sort of daily updates on which experiments ran and if there were any errors or if anything we need to look at. The output and the logs and all the files and all the photos get transferred to what they call the Dropbox on the ISS, which is a Linux machine with that we push files to, and you can get there's quite a high bandwidth connection to that, so that's quite easy to downlink files to Earth. We get syslogs and things, and sort of it was a really surreal experience in April of this year. We were receiving information about what had gone on in the experiments, and we were looking through the syslogs and having to rerun some entries because we'd find unhandled exceptions that we hadn't caught in testing. I mean, literally, it got down to a point where one of them had divided by some variable, and that variable had come from the accelerometer. So on Earth, you're always going to get a constant gravity, a positive acceleration value and g-force value, whereas in flight, it's coming out as a 0, so you're dividing by 0. So I'm sure we can improve our testing procedure to catch things like that, but that's something learned for next year. Then we're able to distribute the files to the teams so that they can start doing their analysis and start working on their reports. Just a couple of, these are the couple of the winners from last year. So this is a team called Firewatchers in Portugal that were using OpenCV to detect evidence of wildfires. They were using open image databases from NASA to compare images they'd taken with previously found ones, and using NDVI, Normalized Difference Vegetation Index, using the infrared camera gives you that extra bit of extra information because you haven't filtered out the infrared channel, so you can get some more information from the photos there, and they were analyzing vegetation and plant life from that which was really cool. And they got, it was really nice to be able to look through the reports and see, the effort that they'd gone to in there, trying to find, a conclusion and trying to work on their further coding perhaps and further investigation that they'd done beyond receiving their data back. Another one, this is a team called the Happy Pi from Poland. They were using, they were analyzing photosynthesis and analyzing observability of underwater life. They got some really interesting photos, so that you can see the kind of fractal nature of the snow on the mountaintops here, and they're looking at the water in these photos. Now, the winners get to have a webinar with a former astronaut, so they can ask questions about what's it like to live in space and ask all sorts of things. So all the winners get together for this, which is a really cool event. So just got a few photos here as I draw this to a close. You get some really interesting cloud. It can be quite disappointing to only capture cloud, but some really nice ones you get back. That one's got a bit of sort of fractal mountain pictures as well. Nice coastline, I think Tunisia there. You get really interesting effects when the sun is in a particular location, because obviously you have, as I say, you can get around the Earth in about an hour and a half. So, and the sun is moving as well. So you've got, you end up with the sun being in a particular place that lights everything up like this. It's a really cool kind of cloud effect as well. This is a selfie I took. Maybe a lot of you are in that picture as well. This one was really interesting. For a short time, this was a UFO until it was identified. One of the teams captured these 3 photos, and we were like, ESA was sort of saying, what is this? What have they captured? And it's actually one of the the SpaceX launchers that was as it was approaching to dock. They just had, they just got perfect timing and managed to capture it in 3 photos. So that was a nice surprise, but very cool. And so one of the other things we've been considering is the addition of a 3rd mission that sort of sits in between Mission 0 and Mission Space Lab. So Mission 0 you can do in, an hour, half an hour. Mission Space Lab, you're sort of working on it all year. Going through the idea phase and writing your code and analysis, kind of a big, lot of time commitment, both for the kids who've got schoolwork on as well and for the mentor, but also in terms of difficulty. So, it can be quite complex to write a program doing a science experiment and logging data and using all these libraries and things. And obviously, working with ESA and working with the ISS operations and requiring crew interaction and things is quite difficult. So something that doesn't involve actually running stuff on the ISS, all the paperwork, if we can reduce that would be good. So we were thinking of doing sort of, we took a load of, we've got a load of data that we've had from previous runs, and that we could run kind of small periodic challenges that people can drop in and out of, and do smaller challenges that we could release. So we're considering something like that, and we'll probably be piloting it this year. So we ran we've got CSVs from 24 hours for 8 batches, 8 3-hour runs on the ISS with all the sensor data, a time lapse of all the photos, so a photo every 10 seconds or so, and all that data compiled along with where the ISS was at the time. So we've got that in mind for what we could for challenges we could come up with for people to find stuff in that data. Now all the student photos are actually on our Flickr. So if you look for the Raspberry Pi Flickr account, that's just full of photos from space, and you can take a look at a lot of those. So how can you help? So come and talk to me today if this is interesting. You can ask me further questions and talk to me about what I've been talking about. And if you're interested in getting involved, I can help you point you in the right direction to getting started. So if you have a young person, you could help them complete Mission 0. That's a really, really simple thing you can do. You just register on Trinket and then get them to write their code and submit it with your code, with your what we call a classroom code, which means that you will be emailed their certificate when it runs. So that's a really simple thing you can do. You just need they just need 2 people in the team to make it a team, and submit their code. If it goes through, it will get run. It will get run in space. You can mentor a group creating a missions space lab experiment, so you can help them pitch their idea and try and kind of make sure it's feasible. And once they get onto their coding phase, you can help them with that. Ideally, doing this as part of a code club or a coder dojo, you've kind of it will give you a good opportunity to do something like this. If you have kids of your own that are at school, tell them their teachers about Asteroid Pi, and you could offer to help run a session in the school, or get them involved some other way. If you tweet, I wish we had Asteroid Pi when I was at school, that would be cool as well. You see more information at asteroidpi.org. All the information there, as I say, it launched yesterday, so everything new just came out, and the competitions are now open. So I will just leave this running while we take any questions. This is 3 hours sped up on the ISS. So you can see it going through a nighttime phase there and going over the Earth.
Thank you, Ben. We've got time for, I think, just one question, because it's never like to let the speaker leave without a question. So if you've got a question, raise your hand.
About the reports and the science, can I read the reports from the students anywhere?
So we've written. There's a blog post about the reports and about us choosing the winners. I don't think we've ever actually released the reports themselves. I definitely think we should. I've suggested it before, but not sort of put enough effort into making it happen. So I will. Yeah, we definitely should. Yeah.
That's all we have time for now. Thank you very much, Ben. Ben's going to be around until Tuesday. Yeah. We'll be available for all kinds of conversations and Raspberry Pi things. So thank Ben once again, please.
Thank you. Thank you, Ben.